Fossil fuel power generation and other industrial processes that create CO2 are a threat to our climate. However, carbon capture and storage is a process by which we can mitigate some of this CO2 emission. And the idea is that you capture CO2 at source, transport it, and you bury it deep underground, about 1 kilometre below the surface, in porous rock strata. And in the UK, most of these storage sites are in fact below the North Sea. However, the development of CCS has been held up to some extent by concern over leakage, and in particular, if there was a leakage, which is thought not to be likely, would it harm the environment? If there was a leakage, what would the environmental impact be? How does the CO2 flow through marine sediments and seawater? And how best to monitor for CO2 if it does leak? So one of the challenges we had was where to situate this experiment. We chose Scotland, in fact, in the vicinity of Oban, because this is where the scientific diving facility is located, but also because there's a wealth of unpolluted coastline, which is relatively well sheltered in the region. We eventually found a site that was perfect. It has ecology and sediments very similar to the North Sea, had the right kind of rock structure to drill through, but most importantly, we could convince the local population that we would take care of their pristine site. And after all, this is very important because it's an area that's highly dependent on tourism. So we held lots of meetings in the locality and briefed the press and put up some information leaflets and created a Facebook page. This worked very well in communicating to people what we were up to. So, once we had chosen our site and drilled our hole, we were in a position to start the science. We started by looking at the condition of the site before we released anything. We needed a very good baseline by which to judge any changes. And once we were satisfied we had got that, we started injection of CO2. Initially very slowly. We had no idea what would happen. We wanted to be very careful that we didn't blow a hole in the sediments. But when we got confident in how the process was working, we upped our flow rate. And in fact, over 37 days, we injected 4.2 tonnes of CO2 into the sediments. Now, initially, we hadn't a clue what to expect. We didn't know if we would see gas bubbles or not. We had some estimates that we would have to wait 100 days for these gas bubbles to appear. In fact, and fortunately, we saw gas bubbles almost immediately. And this began to give us our first clues about how CO2 moves through the sediment. It's actually moving through pre-existing fractures. And then later on we saw the CO2 actually create its own fractures in the sediment. So we certainly saw the typical kind of chemical changes that you would expect from CO2 in seawater. But what was particularly interesting was that these chemical changes were very variable. It depended on exactly how close you were to a bubble plume. You could move 30 centimetres and get a different reading. But it was also affected by the state of the tide. So depending on the tidal mixing, at neap tides there's less mixing and the plume moves not as far as it does at a spring tide where the plume is spread out. And in fact, we can see from models and from some of our results that the tidal movement creates a kind of a circular oscillation around the epicentre, and this is quite a big challenge for monitoring. So we also looked at the biology and the biological response using several methods. Again, some diver observations, but also some cameras that were set up on the sea floor. And we saw a whole range of impacts. Crabs were quite interested in the bubble plumes and seemingly unharmed, whereas urchins were much more sensitive. What we didn't see was a catastrophic impact. We showed that you certainly can pick up CO2, but it's much harder than you thought. So as a result of our work, we recommend that you need to use a lot of different methods. Listening for bubbles, seismic imaging of the sea floor, as well as monitoring for chemical changes. And if you do this, in addition to having a very well-researched baseline, the chances of picking up leakage are really quite good. I think we can show that these real-world experiments are incredibly important ways of advancing our knowledge. But as science always does, it throws up new questions and new challenges. and we certainly have an ambition to repeat the experiment. And in particular, we would like to use it as a test bed for real monitoring tools that would be deployed for CCS to see if they actually work. And there's some scientific questions as well. We saw that a lot of the CO2 was retained in the sediments, and we think it was buffered by calcium carbonate. We don't know how long this buffering would last, and it would be very important to see if this would persist for just a few more weeks or months or even years, because this could really reduce the impact of any CO2 leakage. So we believe that QICS was a very successful project, and it worked as well as it did because we had a fantastic consortium working together, led from Plymouth Marine Laboratory, but especially the Scottish Association for Marine Science, who ran the experiment in Oban. And in particular, we were very fortunate to have a group of scientists join us from Japan who provided their own funding, who joined in the experiment and brought over a lot of extra equipment and manpower, and this has added significantly to what we could achieve. And of course the local people in Benderloch and Oban we should also thank, because they were excellent hosts for the project and put up with us camping on their doorstep for several months.